Welcome back. In our last explainer, we dove into polynomial features and saw how they can make our models way more flexible. But, with great power comes great responsibility. And in machine learning, that means great risk. Today, we're going to face down the two great enemies of any model, underfitting and overfitting. And we're going to uncover the fundamental forces that are really pulling the strings behind the scenes.
All right, so here's our roadmap. First up, we've got to define what a good fit even looks like. Then, we'll meet the two main culprits of a bad model, the simple mistake of underfitting and the complex trap of overfitting. After that, we get to the really good stuff. We'll decode what bias and variance actually are. And finally, we'll see how they're locked in this constant, ultimate balancing act.
So, what is it we're actually trying to do when we build a model? The whole point, the holy grail, is to achieve what we call a good fit. You can think of this as the absolute sweet spot. It's where our model is smart enough to find the real, true pattern in our data, but also wise enough to not get distracted by all the random, meaningless noise.
And that's really the heart of the matter, isn't it? The model's job is to be like a detective. It needs to find this signal, the underlying pattern, while completely ignoring the static, the noise. It has to learn the general lesson from the data, not just cheat by memorizing the answers. Because when you fail to find that balance, well, that leads us directly to our first big problem.
Okay, let's meet enemy number one, the underfit model. The best way to think about this is to imagine you're trying to trace a really complex, beautiful curve, but the only tool you have is a short, straight ruler. No matter what you do, you're just not going to capture the real shape. Your tool is just too simple for the job.
So fundamentally, underfitting is what happens when a model is built on assumptions that are just, well, wrong for the data you've got. It's trying to force a simple, straight line onto a problem that's naturally curvy and complex. And because of that, it just misses the point entirely.
And how do you spot an underfit model in the wild? The dead giveaway is that it's bad everywhere. I mean, it performs poorly on the training data it's already seen, and it's just as bad on any new data you give it. Because it's so simple, it just fails to grasp the key trends.
Now, this problem has a name, a statistical signature, if you will. It's called high bias. In this context, bias just means the model's predictions are systematically, consistently wrong. If you plotted them out, you'd see they're always missing the real data points in pretty much the same way every single time.
All right, now let's swing the pendulum to the complete opposite extreme and meet our second enemy, the overfit model. If the underfit model was too simple, this one is a neurotic perfectionist. It doesn't just learn the pattern, oh no, it memorizes every single dot, every random quark, and all the unimportant noise in the training data.
Overfitting is the classic case of not being able to see the forest for the trees. The model becomes so incredibly flexible that it starts paying more attention to the random noise than the actual signal. And while it might look amazing at first glance, it's actually become totally useless for any real-world task. And this is what makes overfitting so tricky, right? Because when you look at its performance on the training data, it looks like an absolute genius. Perfect scores all around. But the second you show it some new data it hasn't seen before, it completely falls on its face. Why? Because it never learned the rule. It just memorized the answers to the test.
And you guessed it, this problem also has a technical name. We call this high variance. Think of variance as a measure of the model's, well, its jumpiness. It tells you how drastically your model would change if you just trained it on a slightly different sample of your data. A high variance model is unstable, overly sensitive, and just not reliable.
Okay, let's take a breath. We've seen the symptoms, right? Underfitting is simple and consistently wrong. Overfitting is complex and wildly inconsistent. Now it's time to go deeper and diagnose the root causes of all this, bias and variance.
Let's really dig in here. We keep throwing these terms around, high bias, high variance. But what do they actually mean? What's the core idea behind each one?
Okay, bias. Bias is the error that comes from your model being too stubborn, from making assumptions that are just too simple for the real world. It's a measure of how far off your model's average prediction is from the true value. So high bias means your model is fundamentally aimed in the wrong direction, which is exactly what we saw with underfitting.
Variance, on the other hand, is the error that comes from your model being too nervous, too sensitive and flexible. It measures how much your predictions would scatter all over the place if you were to retrain the model on different little chunks of your data. High variance means your model is unstable, which is the classic sign of overfitting.
So let's just put them head to head. You've got bias. That's the error from being too simple and stubborn. It leads straight to underfitting.
And then you've got variance. That's the error from being too complex and sensitive. And that leads to overfitting. They are two totally different sources of error pulling in opposite directions.
And this brings us to the single most important idea in this entire explainer. Here's the catch, and it's a big one. You can't just get rid of bias without affecting variance, and you can't reduce variance without bias creeping back in. They are locked in a permanent tug-of-war. This is the fundamental dilemma in all of machine learning, and we call it the bias-variance trade-off.
And look, this isn't just a nice little concept. It's a mathematical law. A model's total expected error can literally be broken down into these three pieces: the error from bias, the error from variance, and one more piece we call irreducible error.
So think about it like this. Your total error is the sum of your model's stubbornness, which is bias, plus its nervousness, which is variance, plus this thing called irreducible error, which is just the random noise that exists in the real world. It's the part of the problem that no model, no matter how perfect, can ever hope to solve.
And here is that trade-off in action. When you make your model more complex, like when we added all those polynomial features last time, you reduce its bias, you make it less stubborn. But, and this is the crucial part, you always, inevitably, increase its variance. You make it more jumpy and sensitive. You know what? To make this really click, let's use an analogy. Imagine your model is throwing darts at a dartboard. A model with high bias and low variance, that's our underfit model, is like a thrower who is super consistent. All their darts land in a neat, tight little group. The only problem, that group is way over in the corner of the board, nowhere near the bullseye. So it's precise, but it's precisely wrong.
Now what about low bias and high variance? Yep, that's our overfit model. This dart thrower is completely different. On average, their shots are centered right around the bullseye, but they're scattered all over the place. One hits the top, one hits the bottom, another over on the side. There's zero consistency.
And that brings us to the goal: low bias and low variance. This is the pro dart player. Every single dart is aimed right at the bullseye, and they all land in a tight, beautiful cluster right in the middle. This is what we want: a model that is both accurate and reliable. That's a good fit.
So let's just wrap this all up in a nice, neat package. On one side of the spectrum, you have underfitting. The model is too simple, it suffers from high bias, and it's just plain bad at its job. On the other extreme, you have overfitting. The model is way too complex, it suffers from high variance, and it can't generalize to new situations. And right there, in that perfect sweet spot in the middle, is our good fit, a balanced model with low bias and low variance that actually works in the real world.
So we have this beautiful theory. We know we have to find this perfect balance between the forces of bias and variance to get the lowest possible error. But that leaves us with one absolutely massive question. How do we actually measure that error? How do we know if our model is any good on data from the real world, data it's never seen before? Finding the answer to that is exactly what we're going to tackle in our next explainer. I'll see you there.